Hi, this is Greg Conradi Smith. This is part two of lecture 13 on type 1 and type 2 excitability and oscillations in the Morris-Lecar model. In this section, we're going to be talking about type 1 excitability and type 1 oscillations. Now, this type of oscillation was observed in the giant axon of the squid by Hodgkin and Huxley. And in the Morris-Lecar model, what we're going to do in order to get the membrane to behave this way is just make a subtle shift in various parameters, in particular the time constant for the um, dynamics of the potassium current is going to be changed a little bit. All right, so remember that in addition to there being a sigmoidal steady state for the fraction of potassium channels that are open at a given voltage, there's also a function of voltage that's indicating the exponential time constant for relaxation for the activation gating variable of the potassium current, and that's what we're changing here. That's the only thing that we're changing in the model, and it's going to change the phase plane, change the null lines, change the trajectories, and change the type of excitability and oscillations that are observed. So when this change in parameters is made, the Morris-Lecar model ends up in this configuration where there's actually three intersections between the voltage null line, which is red here, and the null line for the activation gating variable of the potassium current, which is green. Right? We'll refer to this first intersection as a stable rest point because it turns out that when a linear stability analysis shows that it's a stable node. This point will be referred to as the threshold because linear stability analysis will show that it's actually a saddle point, and there'll be an important curve here that serves as a threshold for action potential generation. And then this unstable point here is usually an unstable spiral. So you can't know that just from looking at these null lines, but this is what the software like XPP or phase plane would be telling you about these equilibria if you selected them and asked it to tell you what the eigenvalues were. Recall that for a resting stable node, it would say that the eigenvalues were both real and different from one another and negative. For the saddle, you'd have two real eigenvalues. One would be positive and the other would be negative. And for this unstable spiral, you would have a complex conjugate pair of eigenvalues, but the real part would be positive, indicating that the steady state itself was an unstable as opposed to a stable spiral. This plot here is made for a applied current value of about 30. Now, I want to remind you of something that we have said before, but it's going to come up again here, which is that when you have a saddle point in the phase plane, there are these special curves that can be defined that are referred to as the unstable manifold and the stable manifold of the saddle point. So when you do linear stability analysis and you arrive at a saddle, there's going to be these two eigenvectors that correspond to the straight line solutions that emerge from that saddle point. And because the eigenvalues are real and opposite sign, the flow along one of those straight line solutions is going to be inward, and the flow along the other one is going to be outward. Okay, and those straight line solutions are only sort of correct arbitrarily close to the steady state. That's what linearization is doing. But you can trace them away from that steady state, even in the nonlinear system. And that's those curves end up being special solutions that emerge from saddle points that are important and can give you lots of insight into the dynamics. So when you just click on a bunch of points near a saddle in software like XPP or phase plane, you'll see the stable and unstable manifold sort of emerging as a place where there's lots of solutions that are coming together along those manifolds. Note that this is referred to as the unstable manifold here of the saddle. It's called that because you can see from the direction field the flow is away from the saddle point, whereas this is the stable manifold of the saddle because the flow is moving towards the saddle point. Okay, so now in the Morris-Lecar model, when it's in this type 1 configuration, remember I said that the null lines are intersecting 3 times. And now in the background, in purple, I'm actually showing you the stable and the unstable manifold of this saddle point. Now, the stable manifold, one branch comes from infinity and dives into the saddle point in this direction. And then there's another stable part of the stable manifold of the saddle, which is emerging from this unstable spiral and coming in this direction. The stable manifold of the saddle has 2 branches. One is going in this direction and terminating at the rest point at the stable node, and the other stable manifold goes out in this direction, crosses the voltage null line and the W null lines in the correct directions, and then comes back around and returns to the rest point here. So this is a very sort of interesting sort of configuration of the stable and unstable manifolds of this saddle. And one of the consequences is going to be that as long as an initial condition puts you on the right-hand side of the stable manifold of the saddle, there's no way to go back to rest except taking this long excursion around. Now, I say that you have to take this long excursion. I know that from this side, I can't go in this direction because the stable manifold of this saddle is a solution and solutions can't cross, right? So there's going to be no way to move from this side across this manifold and go back to rest in this direction. This fact that the stable manifold of the saddle is connecting this unstable point up here to the saddle in this direction means I have to go around this unstable point before I get back to rest. So this is what Hodgkin and Huxley observed, and Morris-Lecar observed that in their membranes as well. That they called this type 1 excitability. So if you recall that when prior to assuming that the potassium channels were particularly slow, we actually had action potentials of various amplitudes that could occur when the null lines were intersecting in this fashion. In this case, where you have 3 steady states and this separatrix, which is the stable manifold of the saddle sitting here in the phase plane, the action potentials that occur are full-sized. If an action potential occurs, it's full-size. Whereas over here, action potentials, there's sort of a graded threshold, and the action potentials can be different sizes. So 2 fundamentally different types of responses, and that are kind of classified physiologically based on the way the membrane behaves. And here we can see the underlying dynamic reason why the membrane behaves. These types of action potentials are so different. So here's the comparison again. In our initial simulations of the Morris-Lecar model, right, we had this indistinct threshold and action potentials of different sizes that could emerge. Whereas in this type 1 excitability case, if you get an action potential, it comes out full-sized. It just might have a long latency before it occurs. Right? So all or none action potentials are associated with type 1 excitability. Intermediate amplitude or graded amplitude action potentials are indicative of type 2 excitability. We also have type 1 oscillations as opposed to type 2 oscillations in the phase plane. So what we're going to do here, right, this configuration that we drew where the membrane was excitable, right, at rest, you're over here at this hyperpolarized voltage where the fraction of potassium channels is almost all closed, right? A little depolarization over the threshold will give you this action potential and you'll return to rest. But now, what happens if we increase the applied current? So we expect, since this is the gating variable for an outward current, we expect that increasing the applied current actually lifts the voltage null client upwards, and that is indeed what happens. And at some point when this the voltage null client is lifted up the correct amount, this rest point and threshold point will actually touch one another. And since that is a location of the applied current, a value for the applied current, where the number or the stability of the eddy states has changed, this is a critical value of the applied current that's occurring here. Increase the applied current still more, and what you end up getting is this situation where there's one unstable intersection of the null clines and a stable periodic solution wrapping around in this direction. Now, what makes this the signature of type 1 excitability is that when you just get the applied current to be above threshold so that action potentials are occurring, they have this different sort of shape and they occur at an arbitrarily low frequency. So this is actually, this is time in milliseconds. So you almost have 1 second between each of the spikes here. Okay. You also can see that there's a phase of these action potentials where the rate of change of the voltage is really small, right? And that's because if you think about what's going on here, right, the rate of change of the voltage is actually 0 at this point where there's a steady state. And just after the bifurcation, it will also be the case that the rate of change of the voltage is really slow. So this oscillation kind of goes fast and then sort of goes much, much slower as you try to kind of squeeze under this hyperpolarized knee of the voltage null cline. Fast, slow here, fast, slow here again. So this dynamic phenomenon where you're sort of just post a bifurcation, you're super critical of this bifurcation, but you're seeing sort of evidence that the bifurcation just occurred based on dynamics being slow, is that there's a word for that, and dynamicists call that critical slowing down. Slowing down meaning the dynamics are slow, and critical meaning that it's happening just before or just after a bifurcation. So here is the picture of this bifurcation that's occurring, that's leading to type 1 oscillations in the Morris-Lecar model. Remember, the type 1 null clines were set up so that you had a stable node, a saddle point, and an unstable spiral. We're not drawing the null clines anymore. We're simply drawing the node, the saddle, and this unstable point up here. And then we're drawing some special solutions. We're drawing most importantly, the stable and unstable manifolds of the saddle are being drawn. And then remember, the node is flowing in both directions and the unstable spiral kind of sweeping around like this. So this is just a way to sort of get a general sense of what the flow is in the phase plane. And as the applied current changes, this node and the saddle get closer and closer together. And when they touch, the critical point here, this particular fixed point, is referred to as a saddle node because it's sort of behaving like a saddle on the left, right? Because there's 1, 2, 3 trajectories going in here. But on this side, it looks like a saddle point. So on the left, it looks like a node, and on the right, it looks like a saddle. So it's called a saddle node. So just imagine these two getting closer and closer together. When the bifurcation occurs, we have this thing that's called a saddle node point that is has sort of a topology of the flow as indicated here, and it's a very special situation because as soon as these 2 points touch, then a little change of the applied current will cause this steady state to go away completely, right? Now, this type 1 bifurcation that we're seeing here is referred to as a saddle node on an invariant circle bifurcation, meaning that a saddle and the node are coming together, and that's happening on this, they're both on this solution, which is circular, right? So at this point, you can see, invariant circle, what does that mean? It means that topologically we have this solution or sets of solution that make something that's topologically a circle in 2D. So it's effectively a circle, but a little stretched one way or the other. What we mean by invariant is that as you move through the bifurcation, it remains a circle. An invariant set is basically a set of points that if you start on somewhere on that set, you remain on that set. So that's what's true about this invariant circle, is that if you start on it, you remain on it. So there's lots of invariant sets in phase planes. Any fixed point is an invariant set. Stable manifold with a saddle would be also an invariant set, because if you start on the stable manifold, you'll remain on it for all time. We'll maybe talk about that a little bit more in future lectures, this terminology of invariant sets. The particular bifurcation that we're seeing here is new. It's not a Hopf bifurcation, which is the way that the oscillations emerged in the type 2 Morris-Lecar model. But in the type 1 model, the oscillations are emerging through a saddle node that's occurring on an invariant circle. So this is the bifurcation diagram that corresponds to those plots that we just showed. So this axis is the applied current, and you can see that when the applied current is very low, you have stable steady states. That at some intermediate value here, you have stable oscillations that are occurring. And then at very large values of the applied current, you have a stable steady state again. So this would be depolarization block. Now, over here, we have a Hopf bifurcation that is subcritical. So the oscillations that are emerging are unstable. And then that folds back around through limit cycle fold bifurcation here and becomes a stable oscillation. So in this region, these values of applied currents, we have this bistability that we've talked about before, where there's a stable periodic solution and a fixed point separated by an unstable periodic solution. These 3 lines correspond to the subcritical, critical, and supercritical values of applied current that lead to the phase planes that we saw previously. Now, the most important thing about these phase planes, right, are if you consider the invariant circle here, what's going on with the steady states on that invariant circle. So when you're pre-critical, when the applied current is low, there's two steady states. One is stable and the other is unstable. Then they merge to make the saddle node, and then they disappear, right? So that's a saddle node bifurcation on an invariant circle. What you're seeing here, right, when you're subcritical, you have the stable rest point, the unstable saddle, and the unstable spiral. On this side, when you're supercritical, you have a stable, the unstable spiral, and then you have the stable limit cycle, right? So let's go back and check that. When we were supercritical, when we're supercritical, we have an unstable spiral point and a stable periodic orbit. But then when just at the bifurcation point, we have only two steady states. One's the unstable spiral, the other is the saddle node, and then there's still this solution that would be periodic, except you get stuck here. So sometimes people refer to it as an infinite period oscillation, right? Because it would take you, it's an oscillation, you're on this invariant circle, but it would take you an infinite amount of time to leave here and come all the way back around, because the rate of change is zero at this point. So that critical value of applied current and that configuration corresponds to this point here, where basically just when the stable node and the unstable saddle merge to make the saddle node point, when that happens, you have one fixed point, two fixed points. This one's the unstable spiral, and just at that moment, you have this oscillation that's infinite period that's emerging. Now, as the applied current increases, that there's no steady state here, right? And you have an oscillation that isn't infinite period any longer. It has some particular period, but the important thing is that if you move the applied current down towards this location, which is just post where the two steady states have coalesced here, you can have an arbitrarily slow spiking occurring. So this is the picture: pre-critical, rest point, threshold, right? Stable node, saddle point. They merge to make the saddle node here when you're critical, and in the post-critical case, you have the limit cycle oscillation that's occurring. In all three of these, I haven't drawn the unstable spiral that's sitting here in the center. Okay, so now if we consider what would happen when there's a slow passage through a saddle node on an invariant circle bifurcation, well, that's what's illustrated here. If you increase the applied current very slowly, right, you'll get full-size spikes occurring, but they can start at relatively low frequencies. So here the spikes are quite narrow. This is 100 milliseconds between these first two spikes that are occurring. As the applied current increases, the frequency of spiking gets faster, but it looks like if we had balanced the current, like sort of titrated the current just right, we could have got this membrane to spike very slowly. This is gradually changing the applied current until a SNCC bifurcation occurs. And what I'm going to do here is show you, if I can, okay. So we're gradually increasing the applied current. We're not changing the steady state voltage, so that we keep going to steady state voltages that are higher and higher. But then when we get above threshold, do you see how this spike, the first spike that occurs with there being a long period of time where the rate of change of the voltage is low, and then after nearly a second we get our first spike. So this is here the spiking is still pretty slow, and as the applied current increases more and more, they become higher and higher frequency, right? but it's the fact that you can change the applied current to get the spiking to be pretty slow here. Like this is 2 per second. It's the fact that you can do that that's an indicator that you have a SNC bifurcation, a saddle node on an invariant circle bifurcation, and that you have a periodic solution that's emerging with infinite period. Okay, so here's our summary. We had type 2 membranes, type 1 membranes, and when you're talking about oscillations, the important thing was that if you go through a Hawk bifurcation, there's going to be this finite frequency that the membrane, if it's going to spike, it's going to spike at a particular lowest frequency. You can often see what this frequency is just by looking at the spikes as they emerge when you have a slow ramp of the applied current. Whereas the frequency current relation for a SNC bifurcation goes all the way down to 0. So that means that the oscillations are starting with very low frequency or very high period. Here's the characteristic look of the bifurcation diagrams in these two cases. One thing I wanted to say is that this SNC bifurcation is sometimes called a sniper bifurcation. Saddle node infinite periodic orbit bifurcation. Yeah, that'll be it for now. And maybe there'll be a part 3. I don't know.